let's get started. Housekeeping notes. One, again, please sign in. I don't need to do the rant again, but please sign in. Two, I think we kind of covered what we wanted to cover for this quarter. And so the rest of the talks are going to be, I think, very much motivated by what you guys want to see. We're probably going to talk about batch correction and pseudo time. But if you want to talk about, Fairly, can you monitor the chat for me? We're probably going to talk about imputation, or sorry, we can talk about imputation if you guys are interested. We can talk about inferring GRNs. Yes, exactly. Yes, that's I don't. It's a whole thing. You can look it up. If you're interested in it, let us know and we can give a talk about it. Anything else that you guys are interested in? I think that we have 3 weeks, maybe 4 weeks. I don't really know, something like that. I think this is the end of week 6. This is week 7. Good Lord. Okay. It is a week sometime in the quarter. Again, we have ideas, but we want to really hear from you guys. What would you be interested in learning about? Okay, so far, we've covered how to not dissociate data. We've covered how to dissociate tissue, how to generate data, how to sequence that data. Fairly talked about how to align the genomic data. Beijia talked about how to meaningfully reduce the dimensions of the data, and Sam last time gave us a talk on how to QC the data. So today we're going to talk much more about kind of more biology-oriented things. It's going to end up being a lot more about visualization and statistics, I think. But I still think this is going to be incredibly useful. I hope this is going to be incredibly useful for you guys to really get a feel for the underlying data distributions, which is surprisingly non-trivial. This is kind of our outline. It's not very well thought out. This kind of works. Basically, we're going to go over feature plots. We're going to go over clustering and data visualization. We're going to go over statistics, which is my favorite part. And then we're going to talk about heat map. And then I'm going to, if we have time, I'm going to touch on like Go and Enricher and stuff like this. Okay, disclaimer, this is not the truth. This is the truth according to me. I'm happy to defend a lot of the things that I talk about today because I've thought a lot about them. And I really think that this is a better way of thinking about them. I'm happy to have conversations about this. But again, I'm not saying this is definitely not the standard, and this is not the truth. For those of you who are interested, whenever someone says, this is my truth, what they're doing is called observational epistemology. Look that up. Fun fact of the day. Okay, this is a data set that we're going to be using. It's really not relevant to today's talk, but this is the data set. I've like published 2 papers on this right now. Basically, what we need to take away from this is it's human data. It is published. You can look this up. Human data of a skin cancer called basal cell carcinoma, and it is single cell data. I know that they talked about like TCR and stuff like this. We're only going to cover single cell data stuff today. Yeah, I think that's all I want to say here. Pre-processing steps. So I'm not going to read these out. You guys can look at them. What I want to point out is 2 things. One, very little of this is standard. Okay. The defaults are not to filter cells with less than 400 genes. The defaults are not to regress counts, right? Fun fact, in ScanPy, the default is not to use cosine distance when you're doing your KNN graph. I don't know if Beijia talks about that or not. So that's kind of the first point here, is that very little of this is defaults. Second point is, you notice I don't do anything that Sam talked about last time. That's not because I don't believe in it. That's because I didn't know about most of the stuff before you give a talk on it. Which again, that's not saying that's not important. I think this really shows you, like, even if I'm here giving a talk on this stuff, does not mean by any stretch that I know what I'm doing. I would argue that nobody in this field knows what they're doing. Okay, so here's the UMAP. All that I'm showing here are these are all patients. Okay, and I'm just kind of showing you that it seems that the patients are well mixed. So basically, we batch corrected appropriately. That may or may not be true. You could argue it, blah, blah, blah. Okay, I don't want to go over this. So the goal today is identify cell types, right? Like you have all of these dots. Made a very pretty picture. what are the cell types here? Okay. Now, we're going to operate right now under the assumption that not only do I know what the tissue is, I've analyzed this sort of tissue before. And so I know what the cell types I should expect are. And I know what the marker genes of those cell types are, okay? And we're going to define marker genes as genes that are known to be highly expressed in a cell type and lowly or not expressed in other cell types, okay? There's a lot of issues with that definition, but we're not going to cover them again. Again, challenge me on these things after the talk. Okay, so this is what I've got. So this is what we call, I think what Surratt calls a feature plots. Okay, and the basic idea is we have our UMaps, and we color each point, which is a cell, with the log normalized expression of that gene in that cell. Okay, and already what you can see is this guy here is PTPRC. Oh, I guess the Zoom people can't see my. Okay, plan B. Sorry, guys. Okay, so this guy's PTPRC, which marks immune cells. Okay, and so you can see that there's a bunch of immune cells here. There's a bunch of immune cells here. There's a bunch of immune cells here. CD3E are your T cell markers. This guy's for fibroblasts. This guy's for keratinocytes. Blah 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 blah. So this works, I would argue, but it's not very quantitative, right? Like, hey, like this blob over here is presumably T cells, but like, there's not a whole lot you can do with that yet because you can't really tell ScanPy to like subset cells, or like it's not very constrained in a way that allows you to handle the data well. So to make it more quantitative, first we need to group cells. This is kind of what we refer to as clustering, okay? And I'm going to define clustering as grouping unlabeled observations. The very basic idea, Paige talked about KNN, okay. The very basic idea is tell me what the clumps, what the groups in my KNN graph are, okay? This is an example of a type of clustering. This is k-means. We don't do k-means, but you can in other things. And the basic idea, again, is if I tell you here k is equal to 3, these are kind of the clumps in my data. And so now we have 3 different clumps, and we can start asking questions like, how is this clump different from all the other clumps? Okay. So I clustered using Leiden, which is a different algorithm, with a resolution of 0.3, which is the the parameter they use. And so here you see that we have nice clusters. Okay, we still don't have biology information. There's no biology yet, but we do have a way of quantitatively visualizing gene distributions. Okay, I'm going to show you what that looks like for the next few slides, but I really want to introduce a caveat right away. If you haven't seen clustering before, it's very important, especially coming from a biology background, to realize clusters are not necessarily biologically meaningful. Okay. I'm not going to define what biologically meaningful is, because that's a whole can of worms. But what was interesting at the beginning of this field is that people cluster data. They're like, "Aha, we found a new cell type." It's like, no, you didn't. So, not biologically meaningful. Please.
Do you have like an example of like how a cluster would form in a way that is not biologically meaningful? Like what is some factor that you would see driving a cluster to group together that is not based in like biological variables?
So now those are asking me what biologically meaningful is. Okay, no, that's fine. That's fine. We can talk about this because I do think it's important. So the way I would define biologically meaningful is grouped in a way that would make sense to a biologist if you showed them a list of genes that is highly expressed in that cluster versus all other clusters, right? So to give a biology example, if you have a group of cells that highly express ribosomal proteins, and that's the only difference between that group of cells and the other group of cells, I would argue that's not really biologically meaningful. So that's kind of examples. Does that kind of answer your question?
Yeah.
Cool. Okay, so visualization of data. No one uses histograms in this field. I'm just using them because they're nice and easy, and I and I think they really show you the things that I want to talk about. So this is what gene data looks like. So what I'm doing is I'm plotting a gene, again, PTPRC, across all of the clusters, right? So this is cluster 0, this is cluster 1, okay, we got it. There are two things, well, so what's really interesting about gene data, did Peggy talk about sparsity?
Yeah.
Okay, so what we can see here is the sparsity in the data, right? So you have this peak at 0 where you have a lot of zeros. Okay. Oh, I'm sorry. Let me make sure everyone's okay here. So I'm plotting the distribution of data per cluster. Okay, but each point is a cell within that cluster. So I'm plotting the gene distributions in each cell across a cluster. Does that make sense? Yes. One gene.
So it's number of cells that express, or wait, it's counts per cell. And then
It is,
like what's the y-axis and what's the x-axis?
yes. So
Basic question.
yes. So the y-axis is the number of cells in that bin. Okay. And the x-axis, you can see down here, is your log normalized data. Okay. So for instance, here, there are, call it 500 cells that have basically 0 expression of this gene. If you want to look at here, there are 600 cells that have, you know, whatever, 2.1 log normal expression. Does that answer your question? Okay. Okay, so the features I really want to point out here, because they're going to become extremely important, is you have a ton of zeros, and then you have something positive. Kind of looks Gaussian. I'd argue it looks more like a gamma distribution, but that is true for every single cluster. Okay, but each cluster has a different distribution, right? So you see this cluster and this cluster, the distributions look kind of similar, but they're totally separate from this cluster. Okay, that's going to be important again later, and as you move more through single cell. Okay, so pros and cons. Pros, you can see the non-zero and the zero data very clearly. Okay, the cons are your classic histogram cons, which are if you change the size of the bin, it's going to change the interpretability of the data. Okay, I don't have an example of this, but I do have an example later of something similar. And again, this is just to emphasize with this gap, what that means is there are no cells that have an expression between 0 and whatever this tail is, right? So there's literally a gap in the expression data. Okay, again, that's going to become important later. I'm interspersing my code throughout this because I actually think that I didn't know about the get module until like 3 months ago. It's like super helpful. So if you don't know what that is, GTS. Okay, so now let's talk about a way that it turns out we always use in single cell. We just don't call it KDEs. So sorry, I know there's lots of words. This is gonna be a hard slide, guys. So KDE stands for kernel density estimation. And the idea is you're basically finding the empirical PDF, empirical probability distribution function. Okay, so the way to think about PDFs is the area under a point, okay, is the probability of seeing that number in the distribution. Okay. Immediately the math people know what we're doing here is we're assuming a continuous distribution, which again, we do not have in single cell data. We do not have a continuous distribution. We have a peak, and then we have something that, you know, looks gamma or Gaussian. And the absolute height, this number, as far as I know, correct me if I'm wrong, I don't think it means anything. It is what it is, such that the area integrates to 1. But what I would argue is the relative height, okay, means greater probability of that number versus something else, right? So what I mean by that is here the relative height is higher than the relative height here, okay? And that means that there's more probable of seeing zeros than there are of seeing, you know, 5. Okay, but it does not mean that the probability is, you know, 0.25. Yes. Can you speak louder?
Most of the, I guess, all the distributions are binomial. Would it be easier to use binomial distributions? I guess it comes down to what the downstream has, but how much easier? It just depends on the question, but I'm just curious.
We're actually going to talk about that in a few slides. So we are going to start to think about these distributions as bimodal distributions as opposed to unimodal distributions. So hold that question and we'll come back to it later. It's a good question to ask. But the thing I want to emphasize here, because I really think these plots are not interpreted correctly a lot of the time, having a higher probability of something does not mean that there is more of that thing than there is of anything else. Okay, so what I mean is this, right? And again, this is the same distribution. This is just the histogram. This is a KDE. Here, I have more zeros than I have 4, which is just 1, or 5, which is 1, or 6, which is 1. Okay, which means you're more probable to see 0 than you are to see any individual number, okay? But it does not mean that there are more zeros than there are of anything else, right? Here there's like 12, I think, points. So there's more non-zero points than there are zeros. It's just that there are more zeros than any other individual number. Does that make sense to you guys? Is everyone okay? Fantastic. All right. Power forward. And this is just to emphasize that there really is a gap in the distribution. It's like a delta, and then there's something else. Okay, so this is the histogram version. This is the KDE version. Now, pros and cons, I think, immediately. You can still see the non-zero and the zero data. I think it's pretty clear. But the problem with KDEs fundamentally is the same problem that you have with histograms. They don't call it bin width, they call it bandwidth, for different reasons that we're not going to talk about. But what I'm going to show you is it actually kind of changes the interpretability if you're not very careful on how you interpret. And it's also assuming a continuous distribution. Again, sorry, I harp on this, but I think it's important. We don't have this in single cell. This is your example of bandwidth. This is the exact same distribution. This is a bandwidth of 0.2. This is a bandwidth of 0.2. Right? And again, what this is saying is there are more zeros. No, there are more zeros than any other individual number. Okay, but it does not mean that there are more zeros than anything else. Okay. Yeah. Is this clear to everyone? Good? The reason this is important is because it turns out in single cell, we use this plot on a daily basis. We don't call it a KDE. We call it a violin plot. Okay, violin plots are literally KDEs that you rotate 90 degrees and you mirror across the axis. Okay, so this immediately tells us what the pros and cons are. Pros, it's very easy to do, right? Seurat ScanPy has a function for it. They're very pretty, which I'm convinced is the reason why we use them. But again, bandwidth is an issue. I think it's hard to see like zeros and non-zeros. I think it's hard to see if there are very few non-zero numbers, right? This is just an example. Again, this is the same deal with the bandwidth, but just to emphasize this point again and again and again, sorry guys, I know I'm kind of harping on this now. Only 1/3 of the data are zero. That to me isn't necessarily clear from looking at this, right? And you also run into issues where if you have more than like 75% zeros, it's actually hard to tell what the positive numbers are, just because of how they do the KDE. So yeah, I hate violin plots, hatred. So totally biased. Okay, this is a plot that I like a lot. No one uses it for reasons we're going to cover. So this is called an ECDF, or an empirical cumulative distribution function. And I think it's great, but I have to explain what's going on here. So basically, the y-axis is proportion, and the x-axis is your expression, okay? So here, what you can see is, again, approximately 0.3. It's a little higher than 0.3, but approximately 0.3 of your data are 0. Okay, that's how to read this. And that immediately tells you how many zeros you have. Then, if you look at the halfway mark, approximately half of your cells have an expression of 1.2 or smaller. Okay, that's how you read these plots. Again, you could look at called 0.75. 0.75 of your data has an expression of, call it 1.5 or smaller. Okay. So I think these are very nice. Again, it's very easy to see numbers of zeros. It's very easy to see the non-zero distribution. It doesn't rely on what I'm going to very loosely call hyperparameters. So there's no bandwidth, there's no bin width, there's none like this. The con, it's not easy to look at. They're also not pretty. Again, they're pretty ugly plots, which is why we don't use them probably. But the interpretability is hard. I mean, again, these, for example, this guy's a Gaussian, or call it, it's Gaussian-ish. It's not trivial to see that from this plot, right? You have to be able to think about slopes, basically, to see that, right? There's like a slope here and then tips off. Anyway, so manual approved. Again, no one uses these. I love these. Hey, there's an idea. I don't know. I mean, again, I am the only person I know who uses these plots.
I've never seen this before.
Yeah, please.
Do you have an example of like what this looks like in a cluster that is lowly expressed in the name, and then side by side with a cluster that's like highly expressed in the same name?
I don't.
That would be cool.
Yeah. Okay.
Just to see the proportion of zeros, is
I
what you're
want to see
thinking?
what this like looks like when it's like low versus high.
Yeah.
Yeah, you just see like you would see like a way higher spike at the zero. Right?
Yes.
And then it would just quickly go to the
Right, depending on the shape of the curve. Yeah. So I don't have that. That's a good point. But that's the thing, is that you could immediately imagine what they would look like. Right. So it tells you what the zeros are, it tells you what non-zeros are. Yeah. Okay, so tangent number one. Tangent number two, unfortunately, is we still have no knowledge, right? I showed you how to do gene distributions. If you know what the marker genes are and you know what the cell types that you expect are, then you can just visualize your data, you visualize the marker genes in each cluster, as we did with the KDE plots, and then you should be good to go. But let's say you don't know what the cell types are, you don't know marker genes, your PI just handed you this data set and go forth and give me a grant. What do you do? Okay, here's an idea. You can compare each cluster to see which genes are most differentially expressed in each cluster, which really means which clusters have different gene distributions. Okay. In other words, we have to use statistics. Fairly, you're on the chat still. Okay.
It's just all. I'm restating questions in the chat.
Oh, okay. Sorry, you're right. I should do that. Okay, so now I'm going to go through 300 years of statistics in 5 slides. I'm going to talk about, so I want to talk about parametric versus non-parametric tests. So a parametric test, statistical test, right, is you're making assumptions about the underlying distributions of your data. Okay, so the example of a parametric test that we're going to talk about is the t-test. I'm going to talk about what those assumptions are. A non-parametric test is you make either no assumptions or very weak assumptions about your data. The example there is Mann-Whitney U. For those of you in the single cell field, whenever we say Wilcoxon, we're referring to Mann-Whitney U. Very technically speaking, they're different tests. It's a technicality. And then there's some terminology stuff. I'm going to use Gaussian and normal distribution interchangeably, just so that you're not confused. Okay, let's talk about the t-test. Assumptions of t-test. So data are IID, so they're independent and identically distributed. The underlying distributions are normally distributed, okay, and the variance of both distributions are the same. Now, it turns out that I actually wrote these in importance, order of importance from greatest to least. We don't need to worry about this last point at all because there's something called a Welch t-test, which takes care of this problem. Now, the underlying distributions do need to be normal to a certain extent. It turns out that if they have skew, then you can still use the t-test. You just need more data, okay? If you don't satisfy IID, I think you're hosed. What I will say is, it's very plausible that if a cell is expressing a gene, a cell next to it will start expressing that same gene because of the first cell, which means that technically speaking, it's very possible that these distributions are not independent. This is not something we're going to talk about today, but just keep that in the back of your mind. Okay. Why not to use t-tests in single cell data? And today I'm going to pick on people in the audience. Kat, what's going on? Again, are these two distributions different? No, they're not. The t-test says that they are not different with a p-value of 0.8. Okay, let's go to a different distribution. And I want to make the point right away. These two distributions, to me, look like very plausible gene distribution data, right? There's a 0 and then there's things that are positive. Okay, fairly. Are these two distributions different?
Yes.
No, they are not. P-value of 0.5. Uh, 3,000, I think, for both, something like that. Okay, the fuck. I'm going to explain why this is breaking on the next slide, but I just want to make this point because I looked at the defaults a few days ago. The default differential expression function in ScanPy defaults to t-test. Okay, now maybe it's because I'm using an older version of ScanPy. Please, please, please double check. Okay, do not be using the t-test for these data. Instead, you can use Mann-Whitney U or Wilcoxon, and you can see that these gene distributions are very different using Mann-Whitney U. Okay. That makes me cry. All right, so let's talk about why this is breaking. So it turns out that the reason this is breaking is because the averages of these two distributions are basically the same. Okay, and the t-test here, so this is how you calculate the t-statistic, and then you go and look to see if that t-statistic tells you if your data are different or not, basically. The t-statistic relies on the difference of means. So if you have two distributions that have the same mean, basically, it's going to look the same to the t-test. Okay. Now, I don't have a picture of this, but if you think about it, this works very well with normal distributions. It actually works pretty well for unimodal distributions. Kind of doesn't really matter what they look like, although if there's too much skew, then you're in trouble. The problem here, as we were talking about, is that these are bimodal distributions. So it totally doesn't work. Okay, here's the thing. The means are the same, which basically means that the fold change is going to be 0. Okay, the medians are all both 0 because there's more zeros than there are, well, more than 50% of the data are 0. What do? Right? Now there is a little bit of a solution to this, but I want to emphasize log fold change. We're actually going to see this in the next couple of slides. Log fold change using averages. These things are standard. I have literally published papers using averages and log fold changes in this sense. Okay. Now, the suggestion that I have, and the suggestion I think that other people have, is you can actually use what we call the z-score, which is the mean divided by the standard deviation. Okay. Now, first, this basically works, right? So you look at the mean of x or these z-score of x, z-score of x2. They're different. You look at the log fold change. Again, gives you a log fold change of 0.7. And the intuition here is basically you're looking at the average divided by the spread. So the z-score for x2 is going to be smaller just because the spread is greater, right? So this is a solution, but it is an imperfect one, right? For one thing, this number doesn't have any units. It's dimensionless. So how do you bring this back to the biology? I don't know, right? So I suspect that, as we were kind of talking about before, the ultimate answer is going to be treating these two distributions as different distributions. So basically, you have a bunch of zeros, and then you have something Gaussian-ish. But I think what the eventual answer is going to be is we have to figure out how to treat these two things separately. Okay.
About the zero part of the distribution and the non-zero part of the distribution?
Yes. Yes, that is correct. I want to make a quick statement. I don't have this on the slides, but just in case you're not familiar, you're kind of confused. Statistics tells you whether two gene distributions are different. It does not tell you how those two gene distributions are different. Okay, so that's why to use, we use Whitney, Wan, Yu, Min, Whitney, Yu. We know that they are different, but we don't know how. Okay, so you might say, Emmanuel, easy solution, just plot them. Well, in single cell, we need to do thousands of comparisons of a gene across tens to dozens of clusters. You can't plot every combination. So you have to find what the statisticians call an estimator, right? Something that can represent this distribution, something that tells you something about this distribution. I suggest the z-score. Again, the z-score is imperfect, but I really want to emphasize the point, whatever you do, don't use averages. Don't do what I'm going to show you in the next few slides. Okay, so here's the basic setup. And again, this is what is standard in the field right now. So the idea is we're going to ask which genes are most differentially expressed in each cluster. Per cluster, we're going to ask which genes are expressed. And then per cluster, what we do is we calculate the log fold change. And I kind of went over this quickly, but the basic idea is you take the log 2 of the average of gene A in cluster 1, and you subtract from that the log 2 of the average of that same gene in a different cluster. Okay. This is called the fold change. Yes.
Yeah, it's kind of similar to base factor.
It is.
It's like the ratio of marginal. I'm just noting that. You model, right, and compare it.
Well, that's the thing. There isn't really a model there.
Well, I guess if you assume it's like binomial, how different are these models? Are they different? If you marginalize it out, it doesn't matter how big or small the model is.
Right. No, fine. So the question is, this is kind of like base factor. Great. What's your model? Right.
I think that maximizes your parameters to give your data.
Sure. What's your model? Right. But I think this brings up a good point. I mean, I am literally in the process of writing a deep neural net paper on the fact that we can model these things using two different distributions. Non-trivial. It's non-trivial to do. It's doable, right? And you're right. And I think people actually do use Bayes factor in this space. But again, what I'm showing you is this is the standard in the field. Did I answer your question? I guess your comment. Okay. Okay. And then we do something that I'm sure is going to confuse the best out of you guys. Basically, we scale the expression of the gene. So basically, the way about I don't even have. Okay, this is not a good explanation. But basically, the way you scale something is you shift it so that the average is 0, and then you scale it such that the variance is 1. Okay, and there are ways of doing this. I'm not going to go over this, but again, I want to emphasize this only makes sense if you have something that's a symmetric distribution, which we do not have. Okay, I'm betting a lot of you guys are a little confused right now. I want to go over the heat map because I think that'll make sense. Okay, so this is a heat map. Every column is a cell. Every row is a gene. and we are plotting the scaled expression of each of these genes in each cell. Okay. And again, you know, we can have an argument. Yes.
How did you choose what genes to put on that?
That's a good question. So the question was, how did I choose which genes to put in? I didn't, the software did. Basically what you do is you take the most differentially expressed genes. So these were the 5 most differentially expressed genes in cluster 1. These guys were the 5 most differentially in cluster 3. By differentially expressed, I mean, if you use Mann-Whitney U, you compare the expression of that gene versus all the other genes, this is the smallest p-value. More or less what they're doing.
Is it easy to find the differentially expressed genes?
What do you mean?
You know, like you didn't show code.
I did not show code.
Yeah.
It's true. Is it easy? I can show you guys code at the end. I think it's relatively straightforward to do. Again, ScanPy has functions to do that. They also actually have functions to plot this, but it's weirdly non-trivial to do. Anyway, I can show you guys code if you want at the very end. Was there a question over here? Did I see a flop? Okay. Okay, so if you're a biologist or if you're used to looking at these data, you stare at them, and then you notice that a lot of the data I plotted in the feature plot section are coming up here, right? You have your CD3E, PZPRC, you have your fibroblast markers. This is for dendritic cells. Blah, blah, blah. Okay, so again, assuming that you don't know these marker genes, what you can do is you can take the differentially expressed genes, you can sort them by log fold change, which again, we know it's not super meaningful, but you can do this. And then you can, look, honestly, okay, so what people kind of suggest to do is they suggest to use something like Enricher or gene ontology. You can Google Enricher. We're going to talk about gene ontology in a sec. Basically what I did is I took the top 20 genes of cluster 11, I plugged them into Enricher, and what you can see is there's a lot of like endothelial cells, endothelial cells, endothelial cells. These are endothelial cells. But the issue is that even if you do this, if you're not really used to looking at this output, it's super confusing, right? It's like vascular endothelial cells in adrenal. This is like lung. More lung. Remember, this is skin data. No lungs here. So quite frankly, I would almost recommend just Googling each gene, okay? I know that sounds like an idiot idea, but if you go back to cluster, oh, got it, now I have to find cluster 11, which is like the smallest cluster that was smart. Okay, yeah, just by, over here. Yeah, see like ITM3, I think that's a marker for endothelial cells. Right, so honestly, if you Google the top 5, the top 10 genes, it'll probably make more sense than if you try and nurture. That is my claim. Okay, we're almost done. Now I want to talk about, let's say that we have identified, these are T cells. So we identified the T cells, we identified the B cells, we identified, let's see, these are keratinocytes. I think these are the fibroblasts. Okay, let's say you want to compare within a cell type now. So we want to ask the question, among all these T cells, which ones are kind of different? Which ones are doing different things? You know, if you're a biologist or an immunologist, like, where are my CD4 positive T cells, or my CD8 positive T cells, right? The naive approach is to just rip those cells out with the clustering that you did on this KNN graph, okay, and then just do differential expression on these clusters, okay? Please don't do that. The reason you shouldn't do that is because the dimensionality reduction, PCA, if you're using PCA, which most of us probably are, principal component analysis, building the KNN graph, it is relative to the data that you do it on, okay? So Pagia did not cover clustering, correct?
No, but I went over it in the notebook.
Okay.
Briefly.
Okay.
It was rough.
Okay, no worries. Clustering is a whole thing. I don't really have time to get into it now, but basically the way I think about it is if you have 10,000 cells of type A and you have 1,000 cells of type B, you're going to get more clusters in cell type A than you are in cell type B. That doesn't mean that cell type A has more sub-cell types. It means that you have more of that cell type. Like the more data you have, typically, the more clusters you're going to get. So that just kind of gives you an example. Like it's really important to always redo these analyses based on the data that you're interested in looking at. Okay. This is not a perfect example, but what you notice is, so these clusters kind of look similar, you know, like this guy is probably this one. Boom. It's an excellent question. You know, it's funny. I actually read a Nature Methods paper that professed to answer this question. Their solution, Nature Methods, I remind you, their solution was basically cluster stuff, build a machine learning classifier, and then reduce the number of clusters until that machine classifier can accurately classify each cluster. So in other words, we have no idea. Nature Methods. I'm happy to share that paper, but yeah. So long story short, we don't really know. I can tell you the way that I would do it, which is start very small with a very small resolution, okay, and then do heat maps, and then see where those heat maps start to look like basically everything's. It's going to start to look very weird after like too many clusters. That's kind of how I do it. I'm not saying that's the right way of doing it. Again, we covered the fact that heat maps are kind of hand wavy and blah, 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 blah. I don't really know that there is an answer. Honestly. Please.
Yeah, one thing that I tried to say when I was going over clustering was that it requires a priori biological knowledge as well. So like if you're interested in studying like some cell types, then choose a higher resolution because you get more clusters. If you don't care, use a lower resolution because then you know maybe all of the cells of one cell type, regardless of subcell type, are clustered together. So I think that the answer is first that it is unanswerable, but if clustering like the cell type annotation also requires intimate biological knowledge of the system for it. So it's a difficult one. Depends on what question you're answering.
So what Fairley just said was basically you need a priori biological knowledge. I think that that's true. I mean, I'm just going to add to that you know, it's not impossible to find data sets that are like of new tissues, but it's more and more improbable, right? So certainly what you can do is I could go and look at skin data sets and ask, how did they cluster theirs? And did they find any biological significance there? Right, that's certainly one approach that you can use. I actually think that, again, clustering is super hand wavy. There might be better ways of doing this. Okay, we're running low on time. All I'm gonna say is, what we're doing when we're clustering is basically we're trying to get rid of the dropout problem, because it's very hard to compare a cell to another cell if that cell is zero transcripts. I genuinely think that there are better ways of clustering given both a priori knowledge of the biology and a priori knowledge of the distributions. Again, I'm kind of writing a paper on this, but I don't know of any method that actually does that. It doesn't mean much. There's too many methods in this field. But anyway. Okay, so just to wrap up quickly, so what you see, again, this is not a perfect example, but what you see is cluster 7 over here. If I redo all of the steps, I probably didn't need to regress MTs again, but if I redo all the steps, cluster 7 now disappears. Okay, so that's just kind of a hand wavy example. It is important to always always recluster, always redo your KNN, always redo your batch integration, blah, blah, blah. And this kind of goes back to what you were talking about. So basically I reclustered this after doing another dimensionality reduction. I got, call it 5 clusters. And then you can redo a heat map. And the heat map here is actually relatively okay, right? You can see that your, you basically have your like CD8 positive and your NK cells hanging around here. And then you have, I don't know what the rest of this graph is off the top of my head. But I think, oh, these are your Tregs. So this kind of works. And if you increase the resolution, it's going to look more and more like a smear as opposed to like good boxes. Okay. Again, what we're doing here is we're using log fold change on averages. I'm not saying you should do this. I'm saying this is what's built in. Okay. And then you can ask the question, okay, I have these genes, but they're not super informative to me right now. So what you can do is you can take these genes and plug them into what's called gene ontology. And again, you can Google this. And aha, this is my code. I know that there's a better way of doing this. I also don't care. And you can organize them by log fold change. I would recommend doing that. And then you can plug this in. Now you have to be very careful when you're doing gene ontology. Again, this is like practically its own talk by itself, because let's say I don't have any good examples here, but this group. Okay, so I guess what are we looking at here? So you have this tag is associated with different genes. Okay, basically you're asking the question, of the genes that I gave you, how many have this tag, and how many should you expect that has this tag? So basically, is it random chance that you get this many genes that has this tag, or is it not random chance? And again, here, you don't really, this is not a great example of this, but a lot of the times what happens is it looks super, super high. The fold enrichment looks very, very high. That's because you have very small numbers of genes that have been associated with that tag to begin with, right? So if you have 4 genes associated with the tag total, and you have 2 genes out of 100 genes that have that tag, it's going to look very high. Now, is that actually meaningful? Probably not. Yeah, I'm not really going to cover what's going on here. Don't use raw p-value, use FDR. Always. Yeah. So I kind of want to conclude with a little bit of a philosophy note. I mean, really, what I think I hope that you guys are convinced now that the standard tools that we use in single cell, these are things like averages, log fold changes, scaling data, Boolean plots, they don't consider gene distributions, and they're kind of wrong. Now, I would argue that the people who do this stuff that come from a more computational background don't necessarily run into these issues because they already understand them to begin with. Okay. That was certainly not true of me. Again, I don't come from a computational background. I've literally published papers where I show gene averages. Okay. So be warned. I mean, I think really this shows how much more growth is needed in this space. I think it shows how challenging single cell and genomics are. And I guess this is a more practical note, but I think it shows you the power that standard packages have over the field right now. If it's built into a package, the assumption certainly that I make, and that I'm sure other people have made, is that that's the right thing to do. That may not be true. As a matter of fact, what I've shown you is it is not the case. So TLDR, know what your distributions are before you do anything with them. And don't default to the average, both metaphorically and literally, if you're not confident that it'll work. That's the end of my talk. I'm happy to take questions.
Somebody comes from a business background, one thing that somebody, but you know, to everybody, when you think about applying this kind of statistical method to this kind of data, also you need to think that this method has been developed in the centuries for target primarily more specific data problems.
Yes.
If I would measure the range of an actor, there's going to be a value that I'm going to. So when I end up with distribution, that's going to move from when you look at kind of biological data, there's one underlying problem. The expression is a task. There's something some biologists don't want to deal with, but the expression is a task. So even if you consider from a cell, any an infinite precision in the measurement, really not average in the current data, you will still end up in distribution. Because the expression is a task. So when you deal with kind of this process distribution that comes from the intent of the instrument, but also from the intrinsic calculations that we have. I guess I don't really have a suggestion, but my position is if you look about the data, you look at the data, you need to don't take blindly anything that you get from this system. Use your thought, because this test physically is two values. The calculation just comes from the equation, whereas again, if you take a population of cells that are identical,
It depends. So just to restate the question, I guess you're basically what you're saying is in physics, there is a true value and the distribution that you get is due to call it instrument noise, right? But in biology, we have both. We have both instrument noise and intrinsic biological noise. I mean, I think that's totally right. But what I would argue is there are ways of dealing with both things, right? So the example there that comes to my mind is standard deviation versus standard error, right? When you're using standard error, what you're doing is you're assuming basically you're measuring one thing multiple times. That thing isn't going to change. And so you are going to get a distribution from that, but the way to treat that distribution is different from measuring lots of things that should kind of be the same once, right? Which is where you use standard deviation. I would argue that the t-test really does imply that, you know, either there's one true value, which is the mean typically, right, with the central limit theorem, or that mean is meaningful. But I think with Mann-Whitney U, you're not making that assumption. Really, I don't know if you're making any assumptions. You might be. But yeah, I agree that these are questions that I don't know if we've really gotten to wrestling with them yet, right? I mean, this is yeah, yes,
I agree with you that there are really some
yes, yes,
what I think that in some cases the level of knowledge you might have might be such that just because you use knowledge, you know, if you use kind of a statistical test,
they'll look different.
if you just press enter,
Yeah.
you will get the result that they're not statistically significant, but they are themselves. So
Yeah.
this is just a whole long way of saying look at your data and know the data that you're working with. Don't do all the statistical tests the right one. Don't take them as
Yes, yeah. No, and I think that's right. But of course, the issue is a lot, arguably most, but arguably, people who do single cell come from a biology background. We weren't taught this stuff. You know what I'm saying? So good. Other questions, comments, concerns? Boom. Okay.
I consider a space.
Are you gonna ask me what dropout is? I'm gonna throw something at you.
So people will, I think people have like, have theorized first speaking expression distribution. Can you take theoretical first distribution
Yeah.
and take the fact that you take random samples of mRNAs from these
Uh-huh.
and explain the kind of people followed by, then nothing.
It's a good question. So Mike is asking, why is there no values between 0 and, it's typically 0.3, but between 0 and this more, non-zero distribution? Short answer, I don't know. I don't know that it is known. What I will say is the negative binomial, which is typically what people use for count data, for this kind of stuff, even if it's the 0 inflated negative binomial, they don't really explain these distributions. Now you're asking me where it comes from. Again, I have no idea. My guess, frankly, that comes down to sensitivity. Like, I would imagine that we just can't pick up that few transcripts when we're doing our sequencing. That would be my guess. Yeah.
It also just be because you don't really ever look at for genes that are expressed in that manner, because those are not like, those won't show up as your differentially expressed genes, like, I don't know,
What do you mean?
like you're saying that there's not very many genes that have an expression profile that includes stuff between the 0 counts and the positive counts.
Yeah.
I'm saying maybe it's because you just don't look at those genes because they're not super informative.
It's possible. What I will say is, I mean, I've been doing this for 3 years. I can't think of a single gene distribution that didn't have that gap, right? And really
But that's like, I mean, how many genes are you looking at per experiment? Like 100? Like, are you like in terms of violin plots or distribution? Like, there's no way you're looking at all 30,000.
no, I'm not. Obviously not.
I'm not claiming to have seen a distribution that looks like that too, but
Yeah.
I wouldn't deny its existence.
But you could easily check.
Yeah.
And as a matter of fact, I think that gap is real. It's very possible that it just somehow like sampling bias.
I
But
think that it's probably it comes down to the biology though, like transcriptional activation. Like either the gene expression program is on or it's off in the cell. If it's on, it's expressed at a specific level, but like not any, I don't know, not any. And there is some stochasticity in terms of that, but
Yes.
it is either on or off at the regulatory level.
to a certain extent, yes, but I do know that there's also random fluctuations where like transcripts can like just be like one transcript can be expressed. Like we just saw a paper like that in Journal Club actually, where it's just like there's just like one transcript was expressed, right?
Yeah, but I mean, this is also like a consequence of the log normalization you're doing, right? 'Cause
It
that's
very
gonna
much could
shoot
be.
that all the way down to 0 if it's just a few counts. Huh?
So basically, you're suggesting all the zeros as a biological interpretation of not.
I would be the transcriptional program is inactive in that cell. Like, not every cell only expresses a very small subset of genes. Oh, no, I do think there is, but I think that it's important to think back to like biological programs, as fuzzy as they are, like they are 0 and 1, but like there is variation and stochasticity in terms of like capture, detection, degradation of these things. So I don't know.
I have no idea.
I think it's both. I do think it's both. I just think that it's important to remember the biology of how like transcription is activated. Which is fine.
Could we switch like?
Yeah.
Cool.
It's just that we can't detect it being bipolar because of sensitivity issues.
Other questions? Cool. All right, guys. Well, oh, I'm sorry. ECDFs. Is that,
Yeah, I really like the dot plots. I really like dot plots because it shows you how many cells the gene expresses as well as like the average of its expression.
right.
I think that those are particularly useful in visualizing things.
But again, we,
I don't know, what do you think, Sam?
I just like multiple perspectives. So
Yeah.
I would do like on like no one else do the same thing 3 times, but using the feature plots and the heat maps and the dot plot is that's what I would do, but that probably would not make it way to the publication.
That's definitely like you look at all of them and then, you know, you use that information to call the cell type, but doesn't necessarily.
yeah, I think I agree with what they were saying. Like basically you want to look at the same distribution in different ways. Because I think that, you know, I'm making very like binary statements, but like at the end of the day, violin plots tell you something. You know, KDEs, histograms, they tell you something, feature plots, but they're not necessarily overlapping in what they tell you, right? So again, a histogram will tell you how many zeros there are. An ECDF will tell you how many zeros there are, but they won't necessarily tell you other things that may be covered better by the violin plot. I think my whole thing with the violin plot was much more like, hey, like be aware of how to interpret it. The width does not mean number of zeros. So it's more that, but yeah, I think honestly at the end of the day, you're just going to have to plot it different ways. I really think that the future is someone figures that one. And I tried to do this, it kind of worked. But basically, I think the future is someone figures out how to plot these, like really how to think about these distributions in a bimodal way. You have that delta function, and then you have something positive, right? I mean, really, and I think the trivial way of doing that, right, is you look at the proportions of zeros, and you look at the average of the non-zero stuff. I actually think that would work. The problem is that you're looking at, now you have 2 estimators per gene instead of 1 estimator per gene. So it gets kind of gnarly in how you compare them, which again, still could be done, but so if anything, you could maybe do like a dot plot and the Z-score as opposed to the average.
I also want to say that I would not, I mean, I think that it is useful in some contexts to think of the expression as bimodal, but like there are genes that are expressed like everywhere, but like the upregulation of that gene somewhere in particular, so increased expression or increased retention of that transcript or whatever it means on the biological level can be significant in terms of defining the cell type or tissue type or whatever. So I think that there are problems with like thinking about gene expression like that as well.
So, but let me ask you this, right? Did you see this in single cell data?
I'm just saying this is like, I don't have an example to give you at all.
Right, right.
But there are tissues
Right.
that are defined by
Yes,
upregulation of specific genes that's
Yes.
expressed, you know.
everywhere. But again, the assumption that you're making there is that you're not going to see dropout in single cell data. It is my experience that you almost always see dropout.
Oh, yeah. Okay.
Right? So I'm not saying, hey, look, guys, I think the real question we're asking here is single cell data reflective of the biology? Most certainly not. Okay, it is an approximation, right? It's like twice an approximation because we're approximating that A, we capture all the transcripts, B, that mRNA expression directly correlates with protein expression, which is highly dependent on the mRNA and the protein. So, you know, no, but that being said, in my experience, this works very, very well. And hey, the thing about a bimodal distribution, especially if you think about it in this fashion, is if you have a distribution that's normally distributed, that has no non-zero, that has no zero numbers, that's still bimodal. It's just that the peak at 0 is 0. Right? That's kind of one of the nice things about using bimodal distributions. Like if you know where that peak is supposed to be, even if it's not there, technically, it is a bimodal distribution. You just don't consider the zero. There's just no zeros there. Cool. All right, guys, we are way over time. Thank you for staying. I hope that this was useful. I apologize if it wasn't useful. I just confused everybody. But really, the take home is don't use things by default just because you see other people using them. That really is the take home.